Hello students, we will start with the remaining topics of solutions. We have to study one more concentration term, that's called normality. Normality, represented by the letter N. Normality is represented by the letter N. Defined as number of gram equivalents of solute. Defined as number of gram equivalents of solute. Gram equivalents of solute dissolved in 1 liter of solution. Dissolved in 1 liter of solution. Dissolved in 1 liter of solution. Then what is gram equivalent? You should be familiar with the term gram equivalent. That is equivalent weight expressed in gram. Equivalent weight expressed in gram, known as gram equivalent. Equivalent weight expressed in grams. Known as gram equivalent weight. Gram equivalent weight. Then we should be familiar with the equivalent weight. Equivalent weight of acid is equal to molecular weight divided by basicity. Molecular weight divided by basicity. Look into that of HCl, equivalent weight of HCl. 36.5 divided by 1. Basicity is the number of replaceable hydrogen atoms. So that is 36.5. The equivalent weight of sulfuric acid, 98 divided by 2 is equal to 49. Equivalent weight of HNO3, 63 divided by 1, 63, because it contains only one replaceable hydrogen atom. Equivalent weight of oxalic acid is 2C2O4.2H2O. This is called a hydrated oxalic acid. 106 divided by 2. This is a replaceable hydrogen. The value is 63 gram. So these are the equivalent weights of acids. So equivalent weight of acid is molecular weight divided by basicity. We look into equivalent weight of base. Equivalent weight of base is molecular weight divided by acidity. Molecular weight divided by acidity. Example, equivalent weight of NaOH is 40 divided by 1, 40. Equivalent weight of KOH is 56 divided by 1, 56. Equivalent weight of ZaOH twice. The molecular weight is 40 plus 34, 74 divided by 2. So it is 37 gram. So like that you can calculate the equivalent weight of salt also. Equivalent weight of salt. Equivalent weight of salt is molecular weight divided by number of cation into valency of cation. Number of cation into valency of cation. We can call it molecular weight divided by effective charge on cation. Effective charge on cation. So example, I'll give you some example. NaCl, molecular weight M divided by number of cation is 1 into 1, that is 1. So it is M by 1. So M itself. Na2SO4, molecular weight is M divided by number of cation is 2. So 2 into 1, so that is M by 2. Molecular AlCl3, equivalent weight of AlCl3. Molecular weight is M divided by number of aluminum is 1, but the valence is 3. So M by 3. Al2SO4 thrice, aluminum sulfate. Molecular weight is M divided by 2 into 3. So that is M by 6. Equivalent weight of acid is molecular weight divided by basicity. Equivalent weight of base is molecular weight divided by acidity. And equivalent weight of salt is molecular weight divided by effective charge on cation. And the expression for normality is equal to weight per liter divided by equivalent weight. Weight per liter divided by equivalent weight. So this is the expression for normality. And normality is also temperature dependent. Normality is also temperature dependent. I have told you in my earlier class there is volume term, volume is liter. So whenever temperature changes, the volume term changes. That is why as temperature changes, normality is also changing. So temperature dependent, temperature dependent. So normality is also temperature dependent. So these are the concentration terms you have to study. I will repeat all the concentration terms you have to study. The first one is mass fraction, second one is mass percentage, third one is mole fraction, fourth one molarity, then you have molarity, then you have normality, then you have another one called parts per million. And among these, the temperature dependent are normality, molarity, and normality and molarity. These two are temperature dependent. All others are temperature independent. That's all. Now we will go to the next topic, that is vapor pressure. Vapor pressure. So what is vapor pressure? We will see. You are taking a liquid in a vessel, closed vessel. You are taking a volatile liquid in a closed vessel. Volatile liquid in a closed vessel. What is the meaning of the word volatile? Volatile means easily vaporizing. Easily vaporizing. Easily vaporizing liquid. And above the liquid, vapors are present. Vapor particles are present. Vapors. And you know the vapor particles are in the gaseous phase. They are moving in zigzag manner. They collide with each other and they will exert a force per unit area on the sides of the vessel, on the lid and on the liquid. That force applied per unit area is called pressure. So here the pressure is exerted by vapor, so it is called vapor pressure. So I will repeat, what is vapor pressure? The pressure exerted by vapor particle above a liquid in a closed vessel at a given temperature. The pressure exerted by vapor particle above a liquid in a closed vessel at a given temperature, known as vapor pressure. And every liquid has a definite or constant vapor pressure. Every liquid has a constant vapor pressure at a given temperature. Vapor pressure at a given temperature. At a given temperature. As temperature changes, the vapor pressure also changes. We can say vapor pressure is directly proportional to temperature. Vapor pressure proportional to temperature. As temperature increases, vapor pressure also increases. Again, what is boiling point? What is meant by boiling point? The temperature at which a liquid is converted into vapor state. And the temperature at which a liquid is converted into vapor state. And at this temperature, the vapor pressure become equal to atmospheric pressure. Atmospheric pressure. Atmospheric pressure, there is 1 atmosphere or 76 centimeters of mercury, or you can say 760 millimeters of mercury. When vapor pressure become equal to atmospheric pressure, that temperature is called boiling point. That temperature is called boiling point. So we have a relation between boiling point and vapor pressure. Vapor pressure is inversely proportional to boiling point. You write in the reverse also, reverse manner. Boiling point is inversely proportional to vapor pressure. If vapor pressure is very high, then boiling point will be very low, and vice versa. If the vapor pressure is very high, boiling point will be very low. If the vapor pressure is very low, boiling point will be very high. So that's about vapor pressure. So all liquids have a definite vapor pressure at a given temperature, and that is a constant value at a given temperature. That is a constant value at a given temperature. Then we will go to the next topic, that is a law regarding vapor pressure. That is called Raoult's law. Raoult's law. Raoult's law. And Raoult's law is having two types of Raoult's law. Number one, for solution containing both volatile solute and solvent. Containing both volatile solute and solvent. Both volatile solute and solvent. Solvent and solute are volatile. These two components are volatile. Consider a solution AD. Consider a solution AD. Consider a solution AD. A is volatile solvent. A is volatile solvent. And B is volatile solute. B is volatile solute. So we will take the solution in a vessel closed vessel. This is a AB, solution AB. And above the solution, you have vapors of A and vapors of B are present. Vapors of B are present above the solution. Above solution, you have vapors of A and vapors of B. Then, according to Dalton's law, the total vapor pressure P is equal to PA plus PB. P is equal to PA plus PB. Then what is PA and PB? PA and PB are partial pressure of A and B. PA and PB are partial pressure of A and B. Partial pressure of A and B. Then, according to Raoult's law, according to the law, the partial pressure of a component in the vapor phase of solution is directly proportional to its mole fraction. So PA is proportional to chi A and PB is proportional to chi B. This is Raoult's law. So when you remove the proportionality, you have to give a constant. PA is equal to P0A into chi A, and here PB is equal to P0B into chi B. So these two are very, very important. This is Raoult's law, where P0A and P0B are constants of pure A and pure B. Constants of pure A and pure B. Pure A and pure B. Kept alone. So the partial pressure of a component in the vapor phase of a solution is directly proportional to its mole fraction. Or we can say PA is equal to P0A into chi A, where P0A is a constant and PB is equal to P0B into chi B, and P0B is a constant. This is Raoult's law number 1. And here P0A and P0B are constants. They are vapor pressure of pure A and pure B. This is Raoult's law for solution containing both volatile solute and solvent. Both volatile solute and solvent. We will look into the second one, second Raoult's law. Second law is for solution containing non-volatile solute. Solution containing non-volatile solute. Only solvent is volatile. In the previous case, the two components are volatile, but here only solvent is volatile. We will consider a solution AB in a vessel. A is a volatile solvent. And B is a non-volatile solute. And above the solution, you can have only vapors of A. Because B is non-volatile. So total vapor pressure P is equal to PA. And the PA is proportional to chi A according to the previous law. So we can write PA is equal to P0A into chi A. That is according to the previous law. But we know that chi A plus chi B is equal to 1. Then what is chi A? Chi A is equal to 1 minus chi B. So substitute this here in the P0A. In the P0A into chi A, substitute here in chi A. Therefore, you can write PA is equal to P0A into 1 minus chi B. And expanding and rewriting in an order, you have PA by P0A is equal to 1 minus chi B. Then chi B is equal to 1 minus PA by P0A. And finally, you have chi B is equal to P0A minus PA by P0A. This is P0A minus PA by P0A is equal to chi B. So this is Raoult's law number 2. And what is this Raoult's law number 2? That is for solution containing non-volatile solute. We will discuss the term numerator P0A minus PA. What is P0A minus PA? P0A minus PA is a decrease in vapor pressure of A. Decrease in vapor pressure of A. We will consider P0A is equal to 100 and PA is equal to 80. Now this term become P0A minus PA become 20. So this value 20 indicates a decrease in vapor pressure of A. divided by original vapor pressure of A. So we can call this term P0A minus PA divided by P0A, known as relative lowering of vapor pressure of solvent A. Relative lowering of vapor pressure of solvent A, that is equal to mole fraction of solute B. Because of the presence of solute B, the relative lowering of vapor pressure was happened. So this term as a whole, P0A minus PA by P0A, non-binary. I write again P0A minus PA by P0A, known as relative lowering of vapor pressure of solvent A. Relative lowering of vapor pressure of solvent A. Vapor pressure of solvent A. And this is equal to mole fraction of solute B. Mole fraction of solute B. This is Raoult's law, second one. Raoult's law, second. So you have to study two Raoult's law. Number one is for solution containing both volatile solute and solvent, and the second one for solution containing non-volatile solute and only solvent is volatile. So the second one is very important. P0A minus PA by P0A is equal to chi D.